In this video, I'm going to start talking about Bayesian reasoning. So I will start here with sort of a standard example that's often used for Bayesian reasoning. So suppose that the prevalence of breast cancer in the population of women is 1%. And suppose that the sensitivity of a breast cancer test, so its true positive rate, is 90%. Uh, and so people who have breast cancer and get the test, it'll be a true positive 90% of the time. Suppose that the false positive rate is 9%. And so, 9% of the time, if somebody doesn't have the disease, they will get a positive result. And so say we have a woman who tests positive. So what is the chance that she actually has the disease? So Steven Pinker says that the most popular answer from a sample of doctors was between 80% and 90%. So they're guessing that the chances that this woman who tested positive, so she has tested positive, what is the chance that she is actually positive? And they're saying that doctors say it's usually somewhere between 80 and 90%. But the real answer is 9%, which seems, almost absurd to a lot of people. It's like we have this test, and it's 90%. It's 90% sensitive to true positives. So if we test a single woman, what's the chance that she has the actual disease, given that she has tested positive? 9%. That seems absurd. It seems like, why would so many people get false positives if we're saying that the true positive rate is 90%? So how do we know that this is the right answer? And so this is where we actually need Bayesian reasoning. So to get Bayes' theorem, or Bayes' rule, as it's sometimes called, first we want to start with what we already know. So we know that the definition of a conditional is this. So the probability of our hypothesis, which in the above case would be that the woman actually has breast cancer, given the evidence, which in this case would be that the test shows positive, is equal to the probability of actually having breast cancer and getting a positive result, divided by the probability of getting a positive result. And when H and E, so our hypothesis and our evidence, are not independent, remember when we said it's independent if we have P, H, and E is equal to P, the probability of H, times the probability of E. But when it's not independent, then it's the probability of E of our evidence given H times the probability of our hypothesis. And therefore, we have the probability of our hypothesis given our evidence is equal to this right here. And so that is what you will often see as Bayes' theorem or Bayes' rule, which is the P of H, probability of H given E is equal to the probability of E given H times the probability of H, our hypothesis, all over the probability of our evidence. And so let's look a little closer at each of these things. So the probability of H given the evidence, which is the posterior probability. So this is what we're actually trying to calculate here. So this is what we actually want to find. So the probability our hypothesis H is true given the evidence. And so the evidence is, things like the data collected or observations, or in the example above, it would be that the test shows a positive result. So in the above example, E equals test is positive. And so, that is what our evidence is in this case. And then so we have this P, this probability of evidence given hypothesis, and this is called the likelihood. So that's called the likelihood, which tells us the chance that we would observe our data or observation if we assume that the hypothesis H is true. And so that is, telling us what the, sort of what the probability of seeing a positive test is, given that somebody has the actual disease. And then so P, the probability of H, so this is what's called our prior probability. And so this is kind of the one that people often discount, but this is the probability that the hypothesis H is true sort of before examining the data, so before we look at E. So this is what's called the base rate, which I've already touched on in previous videos. And so in the above example, this would be sort of the prevalence of people having the disease, so the prevalence of women having breast cancer among the entire population. And so we can see how that is going to adjust things, because the number of women who have breast cancer in the entire population is going to be fairly small, because most women you meet walking the streets are not going to be women who have breast cancer. And so the probability of E here is what's called the marginal probability. And sometimes this is thought of as sort of a normalizing factor here. So that is the probability of getting the evidence, which we can also think of as breaking it down this way. So the probability of getting the evidence given that the hypothesis is true, plus the probability of given the evidence that given that the hypothesis is false. And so this first one here is kind of the true positive, then the second one here is the false positive. And so the probability of getting the evidence is obviously going to be the true positives plus the false positives, since we said that E is the test is positive. And so the two cases in which the test would be positive is that it's a actual positive, or that it's a false positive. And so you want to be sort of exhaustive of those two things. And so that is what the probability of E is. Then so kind of putting this into words, so we have the probability of the hypothesis being true given the evidence, which is this part right here. Well, no, that's wrong. It was this part here. So that is the probability of the hypothesis being true given the evidence is true is equal to the probability of seeing the evidence given the hypothesis is true. So that is that part right there, times the probability that the hypothesis is true. So times the sort of prevalence of breast cancer in the population in our example, and then divided by the probability of seeing the evidence, which is this part down here, where the probability of seeing the evidence is equal to the probability of seeing the evidence if the hypothesis is true, and the probability of seeing the evidence if the hypothesis is false. And so that is sort of what each of those things in here means. And so let's go back to our medical example. So we said that suppose the prevalence of breast cancer in the population is 1%. Suppose the sensitivity of the cancer test, its true positive rate is 90%. Suppose that the false positive rate is 9%. A woman tests positive. What is the chance she has the disease? So we take our prior here as being 0.01. That's the 1% here. So that's the prevalence of breast cancer in the population. That's our base rate. Then the probability of getting a positive test given the patient has the disease. That's our 90% here, so we give that a 0.9. And then the marginal probability, which is the sum of the positive result for sick patients and the positive result for healthy patients. So for sick patients, that was the zero point 0.9 times 0.01, which is equals 0.009. Then the probability of a positive result for healthy patients was the 9% false positive rate times the 99% of people who are actually healthy, which is 0.891, which I will sort of so I'll just round that up to 0.1 here. And so we do the math here. And so we have the zero point 0.9 times 0.01. So this was our P of E, our probability of E given H, or probability of getting a positive test given that somebody is actually sick, times the probability that somebody is actually sick, and then divided by our marginal probability here. And so when we do the math, that gives us the 0.09. So that's 9%. So the probability that somebody H is actually sick given E that they got a positive test result is 9%. And so to kind of, try to make this even more intuitive, I thought about it in several ways. Well, first, so why do people even the experts go wrong? And this is what's called base rate neglect. And so people are taken in by the high likelihood. So the accuracy of the test being 90%. People neglect the fact that the disease is incredibly rare. So the base rate is very small. So if we look at it this way, so all the people tested is in this black box here. And so these circles are obviously sort of large and exaggerated just so you can actually see it. So the green circle are the people who tested positive, and the red circle is the 1% of the population who actually have the disease. And so we can actually see here there's this sliver of false negatives. And so quite often with these kind of tests like this, it's these false negatives that the scientists want to actually get rid of. Because having a false negative is, the worst kind of possible outcome, because that means that somebody has cancer but they don't know it. Where a false positive is definitely not good, because then somebody is going to probably have to get subjected to uncomfortable and expensive, tests to sort of further confirm, or they might even start getting treatments that they don't need, even like unnecessary surgeries and things like that. And so false positives are not good, but false negatives are definitely sort of the worst outcome that you could get. And so a lot of these tests are trying to reduce the false negatives as much as possible. But this, when I was making this, I thought this was a little bit still not that intuitive, so I went and made this. So let's say we take a sample of 100 women, so just a sample of 100 women, so just grabbing 100 random women, we'll say that it is a random sample, and we want to test all of them with this test for breast cancer. And so when we say that the false positive is 9%, we're saying that, so all the people listed here in black are people who both tested negative and do not have the disease. But you're going to get 9% who are false positives. And so that is the people in blue down here. So that is the false positives. And we see that the person in red is, and so I guess we could, in this case, assume no false negatives. But so the person in red here is tested positive and has the disease. And we see that, this is one person out of 100. So that's 1% of the population. And so we're saying that this 1% of the population of this random sample of women, one of them out of 100 will have breast cancer, and we test them, and they get a positive result, but there is a 9% false positive, and so all these people here in blue also get a positive result, and so those people don't have cancer, but they get a positive result. So then if we sort of zoom in on just these people here, what you see is that 1 out of 10 of them, only 1 out of 10 of those people who tested positive actually have the disease. And so that is a 10%, a roughly 10% of people here who actually have the disease who also tested positive. And so this is sort of the hopefully the intuitive way of thinking about why you would have this sort of really low rate of people, whereas I now I kind of wish I had made the table, but say that that the rate of having the disease is 10%. So say that these people are in blue and red are people who do have the disease, and we still have sort of the 9% false positive rate. So out of 100 people here, we would have, we would still have 9 who are also who also get a false positive. So that would be this right here. And so we take these people here who have the false positive and divide it by the total of number of people. So all these plus all these who are people who got the test and tested positive. You would see that that would be a smaller false positive rate, because we now have these 9 people here out of 100, and then we divide that by the 19. So 9 divided by 19 would be a smaller number, or it'd be a smaller false positive rate. So we see that having that larger base rate, or that larger prior, as we called it, so the larger probability of the hypothesis being true, if that the more that goes up, the lower our false positive rate will be. So we can see why that base rate is actually very important when we are running this calculation. Or even when we're just thinking sort of, in a Bayesian way, and, somebody says, what's the chance that this is happening given that we have this evidence? And, then the thing you want to you want to try to figure out is, what is this base rate? And that can be difficult because a lot of times you don't know what the base rate of something is. And so there are times where you sort of have to guess the base rate, and so that is and I'll talk about that in a future video, which is where you do that sort of Bayesian iterations of, you sort of guess a base rate, you run this calculation here, and then you get a sort of posterior here. Then you take that posterior and sort of put that back in here and run the calculation again, and sort of keep iterating that. But I'll talk about that more in the future. For this, so I hope you found this to be, helpful, and maybe you have a better understanding of what this Bayesian reasoning and what the sort of Bayes' theorem actually means, and sort of what the base rate actually means, and things like that. And I will see you in the next video.